Now we consider thinking of complex numbers in something called polar form. Okay, uh, polar systems take into account not horizontal and vertical movements, but rotational movements. Okay, and so uh, we're going to look at how to convert a complex number from its rectangular form, which we write usually as a plus bi, horizontal and vertical in the complex plane, to polar form. And in polar form, we rewrite a plus bi in terms of its modulus, which is sometimes labeled as modulus of z or r. So it's called the modulus of z if we think of the complex number a plus bi as being z. So we write a plus bi in terms of its modulus and its argument theta. Okay? So how far it is from the origin and the angle it takes to reach the terminal side. And so using basic right triangle trigonometry, we can see the relationship between AB and r and theta. Okay, so let's take a look at this. Let's consider a complex number in any quadrant. So just for the sake of visualization, let's say we are in quadrant 3. So that means we're in the real axis and the imaginary axis, of course. Let's say A is to the left, so this distance is A, okay? And let's say B is down, all right? So this distance is B. So this is the complex number A plus BI. So that's determined by a horizontal and a vertical movement, but we can also describe the location of this point via a rotation. So let's sort of look at the terminal side of this point. We could locate this point by rotating to the terminal side using theta, and then traveling this distance from the origin to the point along this theta path. So that distance is our modulus r. Okay, so what is the relationship there? Well, what we can see, so by the way, this distance here, let's do this in green maybe. This horizontal distance is our A distance, and this vertical distance is our B distance. So what are the relationships here? Well, A actually ends up being the hypotenuse r times the cosine, because it's the adjacent side, times the cosine of the argument theta. And B happens to be the hypotenuse r times, since it's the side opposite angle theta, r times the sine of theta. And so what we end up finding out is that a plus bi is the same thing as, well, I can rewrite a as r times the cosine of theta. So I'm changing from a and using my r and my theta, my modulus and my argument to describe my a value, okay? Plus b which is r sine theta times I. And so if we kind of look at this further, what we have then is r cosine theta plus, and then, so I don't confuse, I can drop these parentheses because this is all multiplication. I don't want I to look like it's part of my angle theta I. That would be kind of strange. So typically we'll put the I up here in the front. So it'll be r cosine theta plus I times r sine theta. Okay? And then finally, because these have an r in common, we will usually factor the r out to get r times the quantity cosine theta plus I sine theta. And so this is the polar form of the complex number a plus bi, and all we've done is written a using r and theta, and we wrote b using r and theta, and then we factored the r out to separate the modulus from the trig functions. Okay? So let's do some concrete examples where we do this conversion from a plus bi to r times the quantity cosine theta plus I sine theta. One thing you'll notice about the polar form, however, is that the modulus, or sorry, not the modulus, the argument, the angle theta, is the same for the cosine function and the sine function. That has to be true, okay? So let's go look at a couple examples. So if I want to convert this to polar form, it might be good to draw a picture of it, okay? So let's graph this complex number, my real axis, my imaginary axis. So I go left 9 on my real axis and down 9 on my imaginary axis, and I get this complex number here. And so what excuse me, if I look at sort of this right triangle that's formed, I can tell that my reference angle here, since this side is -9 and this side is -9, that's right, that's my A and my B, I can tell that my reference angle here has to be 45 degrees because those two sides are equal, which means that my theta is going to be, I'm going to rotate to pi, and then I'm going to rotate one more pi over 4, so theta equals 5 pi over 4. Okay? And r is going to be the length of the hypotenuse up here, so I'll have 9 squared is 81, plus 9 squared is 81 again. So 81 plus 81 is 162, and take the square root of that. So my r is the square root of 162. So how do I get my polar form of this? So I'm going to rewrite -9 minus 9i. And what I want to do now is think of -9 as being my hypotenuse, which is square root of 162, times the cosine, because it's the adjacent side, of my theta, 5 pi over 4. So that's how I rewrite the -9 from the real part of my complex number. So I can rewrite that as square root of 162 times the cosine of 5 pi over 4. So that's the a part of my a plus bi. Notice there's no negative here. That's because the cosine of 5 pi over 4 is negative. So the negative is built into the trig function. And then what I need to do the same thing for my vertical side, which will be my hypotenuse square root of 162. And since it's the opposite, or the vertical side, it's going to be times the sine of my angle, 5 pi over 4. Okay, so I can take my -9 from my original complex number and rewrite it as plus, because this is positive, again, the negative is built into the trig function, plus square root of 162, which can be simplified, by the way. I'm not concerned about that. Maybe books would require you to simplify it. You could do it on a calculator, different things like that. But I've got the square root of 162 times the sine of 5 pi over 4. That represents the -9. Okay, and then I just need that multiplied by my I. So I'll take this times I. And as we saw before, you can drop the parentheses and you can factor out the square root of 162, which would leave a cosine of 5 pi over 4, plus, remember we write our I in the front so it doesn't get grouped in with the angle, plus I times the sine of 5 pi over 4 is all that's left. And so this is the polar form of the complex number -9 minus 9i. And if you actually calculate the cosine of 5 pi over 4, calculate the sine of 5 pi over 4, and distribute the square root of 162, you will get -9 minus 9i. You could check that for yourself. Make sure your calculator's in radians mode if you're using a calculator. Okay, let's do the next one. Should go faster, but it's tricky because it's just 15. So I want to convert this to polar form. This is the same thing in rectangular form as 15 plus 0i. So let's draw a picture of that. 15 plus 0i, well, I go 15 out on my real axis, which puts me right here. So here's my complex number. My theta is on the positive real axis, so theta is 0. There is no rotation involved. Okay? And then r is how far from the origin I am, so r is 15. Now, this one can be tricky because there's no right triangle, but what I want to do is write 15 as 15, so this is, since it's horizontal, it's going to be my r value 15, which behaves like the hypotenuse, and since it's horizontal, it would be multiplied by the cosine of my angle theta, or 0. So that is how I can rewrite my 15 from up here. So 15 plus 0I, in polar form I'll write my 15 as 15 times the cosine of my angle, which in this case is 0. Then I need to write my vertical component in terms of r and theta as well. Well, the vertical component, there's no triangle so I can't actually see it, is going to be r, my hypotenuse if you will, 15 times the sine of my angle 0. And that's how I can write my 0 from my rectangular form. So plus 15 times the sine of 0 times I. Now, this is a little tricky, right? Because you can't see a triangle. There's no hypotenuse actually, so we're really basing this on r, which behaves like a hypotenuse. But verify for yourself. Get a calculator out and take 15 times the cosine of 0. You'll see that it's equal to 15. And take 15 times the sine of 0 and you'll see that it is 0 in fact. Okay? Now, you're probably wondering, why in the world would I want to write it this way? Well, there are advantages that I cover in other videos. But the idea is we're using the r and the theta here to describe this complex number. Okay, so finally, if you drop these parentheses and factor out the 15, the r value, you're left with cosine of 0 plus, put the I in front, I times the sine of 0. Okay, and that is the polar form of the complex number 15.